Can you hear me? Okay, I'm going to go ahead. I've made a few notes, and I'm going to go ahead and share my screen so you can start writing those notes while we wait for the others to join us. Today we're going to start chapter 10. So we're going to be on page 400 is where we'll start. So you can go ahead, if you're taking notes, take some time to write this down. John, is that you on the phone? I see somebody's called in. Who is that?
Caitlin.
Okay. We'll wait a few more minutes. We've only got a little more than half of us here right now, so we'll wait a few more minutes before I actually get started. I haven't started yet. I'm just giving you some time to write down notes. Okay, we'll go ahead and get started. I'll go back to that first slide in case you didn't have a chance to write all this down. And of course, I am recording, and I will send you the links to the recording. So our focus now is going to shift to gases. So we're going to be in chapter 10, page 400. And we're going to look at some of the properties of gases. We can study these pretty much as easily as we study the properties of solids and liquids. But a couple of things about gases. While they are very different chemically, they are very similar in their physical properties. So we can have gases that are very different chemically, made up of different chemical elements that still share some of the same physical properties or very similar physical properties. All gases are nonmetals, or made up of nonmetals, and their molecular formulas are pretty simple. So that means they have a smaller molar mass than what we would consider with solids or liquids. I mean, we have looked at several solids and liquids. For example, sucrose is one that we've worked with some in some of our stoichiometric calculations. And we know that sucrose is a huge molecule, and so it has a large molar mass. But when we look at gases, our gases are pretty simple. They may only be composed of one element. They may be 2 or 3 elements, but small numbers of each one of those. So we're going to have small molar masses for our gases. Now, if we look at how gases differ from solids and liquids, the first thing that we have to look at is that gases expand. When we put gases into a container, whatever that container is, the gases will expand to completely fill the container. So the volume of a gas is going to equal the volume of the container. So when we're looking at these problems and we're working these different problems, then you'll see the volume of a container. We take that to equal the volume of our gas because we know that the gas is going to expand to fill that container. So if we have a 2-liter container, then we will have 2 liters of gases because they expand. The second thing is that kind of the opposite, they're also highly compressible. So if they can expand, They can also be compressed. So gases are highly compressible. When pressure is added, volume decreases. So when we have our gases in this container and we start to increase the pressure. So basically what we do is we can have some type of a container where we can compress the top of it. Okay, so think about like a bicycle pump. Okay, so we've got that canister that's got air in it, right? And push that lever down, you are increasing the pressure that is within that container, and so your volume is decreasing. Now the space for the gases is not as large, and so we're not going to have as high volume because the area in which they can expand is smaller. Two or more gases form a homogeneous mixture regardless of the identities or proportions of the gases. Okay, when we put liquids together, okay, for instance, oil and water. Okay, if we put oil and water together, we know that oil and water don't mix. They form a heterogeneous mixture. But with gases, it doesn't matter what gases we put together. When we put two or more gases together, they mix and form a homogeneous mixture so that you can't tell where the individual molecules are. An example of this is the atmosphere that is all around us, right? So we know that there are a lot of different gases that make up the atmosphere. We've got oxygen and nitrogen, we've got argon, we've got water vapor. We have a lot of differences, and they mix and mingle to form this homogeneous mixture. So that every time we take in a breath, we're getting this mixture of gases. We're not in one breath getting more oxygen and then in the next breath getting more nitrogen. Okay. Gas molecules are relatively far apart. That's what allows them to expand. When they are compressed, when we add pressure, it forces them to come back together, which is why the volume decreases. And this is also why they can form a homogeneous mixture. With our gas molecules being so far apart, each molecule kind of acts on its own. And that's why different gases can be relatively the same, because the gas molecules have very little interaction with one another unless we force them to. So unless we put them in a situation where they are forced closer together, like we increase the pressure, for instance, or decrease the volume, then the gas molecules have very little interaction with one another. Now, one of the properties that we look at for gases is pressure. And pressure is the force that acts on a given area. Okay, so our formula there, you see pressure equals F divided by A. So force divided by area. That is our formula for pressure. And so gases exert a pressure on any surface they contact. So if we think about a balloon, okay, so you've got a balloon and you inflate that balloon, whether you use helium or you just use your own hot air to blow up that balloon. When you put the gases in that balloon, those gases exert force or exert pressure on the inside surface of that balloon. Okay, and the pressure that they exert is equal to the force divided by the area of that balloon. So gases exert this force. We can divide that by the area of our balloon and determine exactly how much pressure is being exerted on that balloon. But we also have pressure that's being exerted on the outside of the balloon by the atmosphere. Okay, so those gases within the atmosphere exert pressure on the outside of the balloon. So we have opposite forces, opposite pressures. Okay, so we can calculate the atmospheric pressure. We can calculate how much force is due to the gases that are pressing in around us, And so the atmospheric pressure is equal to the pressure exerted by gases in the atmosphere. And we can calculate this using two different equations. Okay, our force equation, which is F equals ma, where m is mass and a is acceleration, and pressure we know is equal to force divided by area. So we can put different numbers in these equations and figure out how much pressure is being exerted by those atmospheric gases. So if you look at page 401, there is the attempt here to kind of show you where these numbers are coming from. So if we use, our first equation, force is equal to mass times acceleration. So this is mass times acceleration. And basically when we're talking about acceleration here, we're talking about gravity. Okay, so we're talking about the gravitational force. And that's a constant. Okay, so we're going to plug in what we're going to look at. If you look at the bottom of page 401, figure 10.1, we've got this column of gases. Okay, it's a 1 meter by 1 meter column of gases. Okay, gravity is acting on this column of gases, and this area of our gases is 1 meter square. 1 times 1 is 1 meter squared, and the mass is about 10,000 kilograms. So we're going to plug this into our equation, and we're going to say we have a 10,000 kilogram column of air, and we're going to multiply that by our gravitational constant, which is 9.8 meters per second squared. Okay. And when we do the math, and when we get our significant digits with a little bit of rounding, we have 1 times 10 to the 5 kilograms times meter divided by second squared. Okay, so all we did is take the mass of our column of air, okay, and multiply that by our gravitational constant. And we end up with this number, 1 times 10 to the 5 kilogram times meter per second squared. Well, this unit right here, kilogram times meter divided by second squared, is equal to the Newton, or N. Okay, and this is the SI unit for force. Okay, named for Isaac Newton. So 1 Newton is equal to 1 kilogram times meter per second squared. So our force here being exerted by our column is 1 times 10 to the 5th newtons. Okay, so that's how much force is being exerted by this column of air. So now we're going to take this number that we have derived here, our force, and we're going to plug it into our other formula. Okay, we're going to plug that into our pressure formula. So pressure is equal to force divided by area. Okay, so we have 1 times 10 to the 5th newton. And we've said that our area, because it's a 1 meter by 1 meter column, is 1 meter square. And that gets us to 1 times 10 to the 5th newton per meter square. Okay, well, this unit here, newton per meter square, okay, is equal to a Pascal. Okay, so that's equal to a Pascal. And the Pascal is the SI unit then for pressure. Okay, so the pressure exerted by this column of air is equal to 1 times 10 to the 5th Pascal. So this is how much pressure is exerted by this column of air, so by the atmosphere. Okay. A related unit, and you're going to see we have lots of units for pressure. Okay, so a related unit is the bar. Okay, and the bar is equal to one times 10 to the fifth Pascal. So essentially, 1 bar is equal to 10 to the fifth Pascals, or 100 kilopascals, because we can divide this by 100, or divide this by 1,000 to get kilos, and so 1 bar is equal to 100 kilopascals. But we have another unit that we often use, which is pounds per square inch. You know, if you're airing up your tires, okay, whether they're bicycle tires or the tires on your truck, we have a PSI, pounds per square inch. And so this is also equal to 14.7 PSI, which is pounds per square inch. Okay, that one's one that we're a little bit more familiar with because it is associated with something that we know, that we've heard of. So we can use these units interchangeably, and as we start working our formulas, you're going to have to get used to converting between these different units. So 1 bar is equal to 100 kilopascals, and of course Pascal is our SI unit, our official SI unit. We don't use it very often, but it is the official unit. And that's equal to 14.7 pounds per square inch. Okay, now this is at sea level. We're measuring here at sea level, and so most of what we do with our calculations will be at sea level, or we assume that we're at sea level unless we're told otherwise. Okay. Now, we can get into a little bit more detail with pressure, and look at the work by Torricelli. So Torricelli was actually a student of Galileo's back in the 1600s, and he was really the first person to show that the gases around us, that the atmosphere had weight. So he was able to demonstrate that the atmosphere had weight, or had mass. And he developed or invented the barometer, okay, which we still use today. His barometer, okay, you can see it there on page 402. Basically, he has a glass tube that is more than 760 millimeters long, closed at one end, opened at the other, and completely filled with mercury. And then it's inverted into a dish of mercury. So no air is in the tube. We just have this dish of mercury and this column, this glass column that is also filled with mercury. When the tube is inverted into that dish, some of the mercury flows out, but some, as you see there, demonstrated on page 402, remains in the tube. And so what he said is that the mercury within the dish has pressure exerted upon it by the atmosphere, okay? And as it is experiencing this force, okay, this pressure, that keeps mercury in the tube, okay? And that pushes the mercury in the tube until the pressure of the column of mercury in the tube is equal to the pressure of the mercury in the dish, okay? So the height of the mercury column in the tube is equal to the atmospheric pressure. And as atmospheric pressure changes, the height of the column changes, okay? So he definitively exhibited that the atmosphere had weight and therefore had force. Okay, it had pressure. And so as the atmospheric pressure is pushing down on this dish of mercury, it forces mercury up into the tube. So the higher the pressure, the higher the column of mercury inside the tube. Okay, the lower the pressure, the lower the column of mercury inside the tube. So he published his ideas, mass opposition. Okay, people didn't want to believe him. This, again, keep in mind, this is the 1600s. Okay, but Pascal, again, who studied pressure, he got his hands on one of Torricelli's barometers, and he actually carried it to the top of a mountain and compared what happened to the height of the column of mercury at the top of the mountain versus down in the valley below. And as the barometer was carried up, the column of mercury, the height of the column of mercury started to decrease. And that's because as we go higher and higher, the amount of force exerted by the atmosphere is less. Okay. And so he said, yeah, this has to be the case. This has to be measuring the force exerted by these gases in the atmosphere. And so this led us to develop what we refer to as standard atmospheric pressure. Okay. So we developed this notion of standard atmospheric pressure. Okay. So this is the typical pressure at sea level. So again, we're measuring at sea level. That is what all of our measurements correspond to. And this is the pressure that is significant enough to support the column that is 760 millimeters of mercury high. So when you've heard the weatherman talk about pressure and he's used these units of millimeters of mercury, that's where it comes from. It comes from this column of mercury that at standard atmospheric pressure, that column of mercury is 760 millimeters high. Therefore, 160 millimeters of mercury. Okay. So that is our standard atmospheric pressure at sea level. Now, in SI units, okay, this 760 millimeters of mercury is equal to 1.01325 times 10 to the 5th Pascal. So it's a little bit higher than what we had looked at before. And so we use some non-SI units to define gas pressure, such as the atmosphere, the torr, the millimeters of mercury. So I'm going to put all of these out here for you. And if we were in class, I would give you what I refer to as my gases cheat sheet. So since I can't do that for you, what I encourage you to do is take a piece of paper, a clean sheet of paper, and write at the top of it, gases cheat sheet. And we're going to add some things to this that are going to be very, very helpful to you as you work on these gas problems, because the majority of what we're going to look at from here on out in chapter 10 are problems. Okay, we're going to be doing a lot of calculations. So here's our first thing. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr. Okay, so we named that unit after Torricelli. Okay, and that is equal to 1.01325 times 10 to the 5th Pascal, or 101.325 kilopascal, 1.01325 bar, and 14.7 psi. So this is going to allow you to convert between all of these different units. So if pressure is given to you in kilopascals and you want to know pressure in torr, you can set up a conversion and figure that out. Okay, so make sure you get all of these down. These are also in your book on page 402, but it's worth having all in one place. All of these different pieces of information I'm going to give you. It's handy to have them all in one place, and I'll keep adding to this gases cheat sheet as we go through. So I'll give you a second to get that written down. Just give me a thumbs up in the chat box when you've got it all. Or when you're ready for me to move on, if you're going to take this from the recording later. Oh, okay, looks like you've gotten it. So let me go back here and let's just do a conversion. So go back to where you were taking your notes if you want to, and leave your gases cheat sheet alone. We're going to add some more to it. But to give it some thought, on page 402 gives us a pressure of 745 torr. And it asks us to convert this to millimeters of mercury. Well, torr and millimeters of mercury are equal units. So 745 torr equals 745 millimeters of mercury. Okay, they're the same unit. So there's a 1-to-1 ratio between torr and millimeters of mercury. B asks us to convert that to atmospheres. Okay, so now we're going to have to use a conversion. So we're going to start with what we know, 745 torr. We know that 1 atmosphere is equal to 760 torr. So I'm going to set up my conversion this way, so that torr is on the bottom, so that I can cancel that out. And then I say 745 divided by 760. And I get 0.980 atmospheres. So then I have to ask myself, does this make sense? Well, I know 1 atmosphere is 760 torr. I have a little bit fewer than that at 745 torr. So yes, my answer of 0.980 atmospheres makes sense. That's almost equal to 1. So that would be an answer that made sense. Part C asks us to go to kilopascals. Okay. So again, I'm going to start with what I know, 745 torr. And in this one, if I'm looking at kilopascals, I know that 101.325 kilopascals is equal to 760 torr. Okay. So when I'm doing these conversions, I'm always going to set them up where what I'm looking for is on the top here, and what I have is on the bottom, so that I can cancel it out. Okay. So I'm going to say 745 times 101.325, and I'm going to divide that by 760, and I get 99.3 kilopascals. Again, I'll look at that. Does it make sense? Yeah, it makes sense. If 760 torr are equal to 101 kilopascals, then 745 torr is going to be close to that. So 99.3 makes sense. And then they asked me to convert to bar. Okay. So again, I'm going to say 745 torr and 760 torr on the bottom and 1.01325 bar on the top. My torr cancels. So I'm going to say 745 times 1.01325 divided by 760, and I get 0.993 bar, which is equal, or which answer makes sense because that's a little bit less than the 1.01. Here's the key thing to remember here, guys. Always include your units. Excuse me. Always include your units, okay? And always read your problem very carefully to determine what units you have. That is one of the main ways that students get tripped up on these questions, okay? Look at what you have, look at what's being asked for, and make sure that you do the calculations correctly and make sure you include your proper unit, okay? And as usual, I'm going to want to see all your work as you're working these so that I can give you partial credit. All right. So now if we jump over to 404, we're going to start looking at the gas laws. And so in your video that you watched, your Ed Puzzle, you got some introduction to some of the gas laws and some of those calculations or some of those formulas that we're going to be using a lot of. So the first gas law that we come to here in the book is Boyle's law. And Robert Boyle was a British chemist, and he studied the relationship between pressure and volume. Okay, so he studied the relationship between pressure and volume. And as we've seen already, gases expand and gases are compressible. Okay, and so that helps us define our relationship. Okay, so the volume, what he said, okay, is that the volume of a fixed quantity of gas, so we're looking at the same amount, so 2 liters, for instance. So the volume of a fixed quantity of a gas at constant temperature, and as you saw in the video, we really can only look at 2 variables at one time. For the most part, we're going to look at a couple of scenarios when we consider more than one. For the most part, we're going to look at 2 variables while the other 2 are held constant. Okay, so we've got a constant quantity, so a fixed quantity, and for Boyle's law, we have a constant temperature. So the volume of a fixed quantity of a gas at constant temperature is inversely proportional to the pressure. Okay. And so you get this notion of what we call a constant. And so in the video, they use a K, and that's kind of what we use. This is just some constant. This is just some number. And what this does is it allows us to set up an equation that allows us to look at a, initial and final type of scenario. Okay, So we're going to be able to look at what happens to a gas initially, and then what happens to a gas as its pressure or its volume change. And so we can derive an equation from this. And I'm going to go back up here to my cheat sheet, and I'm going to add my first equation here. So we're going to add the Boyle's law equation, okay, where P1 V1 is equal to P2 V2, because P1 V1 is equal to the constant K, and P2 V2 is equal to the constant K, so we can set them equal to one another. Okay, so what's going to happen in these types of equations is you're going to be given 3 of the 4 values. Okay, so you may be given P1, V1, and P2 and asked to find V2. Okay, or you may be given P1, P2, V2 and asked to find V1. Okay, so this equation is very similar to our molarity equation that we looked at last week, or I guess it was week before last now. Our M1 V1 equals M2 V2. It's the same concept here. Okay, Boyle's law is the same concept. Okay, so let's look at a problem here. So I'm going to find us a problem. Well, I'm having trouble finding us a problem. Hang on a second. Okay, I'm not finding any good problems there. Hang on a second. Your book goes really into detail with the ideal gas law that we're going to get to on Tuesday, but it doesn't have very much about the other gas laws in here. So I know I've got some practice problems somewhere. I'm just trying to find them. Okay, here we go. All right, so we have here we go. All right, so our problem is to calculate the final volume when 125 milliliters of argon undergoes a pressure change from 705 millimeters of mercury to 385 millimeters of mercury. Okay, so we have 125 milliliters of argon. Okay, oops, not. Argon gas. Okay, so that's our volume, and that's going to equal V1. Okay, they're telling us that we have 125 milliliters, so that is my initial volume. And then I've got a pressure change from 705 millimeters of mercury. Okay, so that's my P1, because that tells me I have an initial, or the problem tells me I have an initial pressure from 705 millimeters of mercury to 385 millimeters of mercury. And so that is equal to my P2. So the only one lacking is V2, so that's what I have to be looking for. All right, now, a few things about working these problems. It doesn't matter specifically when we're working the Boyle's Law problems. It doesn't really matter specifically what units we have as long as they're the same. Okay, so in this problem, we have our pressures in millimeters of mercury. That's okay, because they're both in millimeters of mercury. If they weren't, then we would have to do a conversion and get both of our units in the same unit. Okay, so we'd have to get both of them in the same unit. So if one of these was atmospheres and one of them was millimeters of mercury, then we would have to pick which one are we going to go with. Okay, and then just do a conversion. So it doesn't matter what units you have for these Boyle's Law problems as long as they're the same. So our equation P1V1 equals P2V2. I am looking for V2. So I'm going to get it isolated and by itself. So I'm going to divide both sides by P2 so that I have my equation V2 equals P1V1 divided by P2. And so now I'm going to plug these in. So my initial pressure, 705 millimeters of mercury. My initial volume, 125 milliliters, divided by my final pressure of 385 millimeters mercury. Units of millimeters per mercury cancel out. I'm left with millimeters, which is correct because that is a volume. Now, before we work this, I want y'all to think about what's happening. So pressure and volume have an inverse relationship, meaning as pressure goes up, volume goes down, and vice versa. So in this problem, our pressure is going down. So what should we expect to happen with volume? Yes, our volume goes up. So if pressure goes down, volume goes up. So we should expect that our answer is higher than 125 milliliters. So in these types of problems, that's how you're going to know if your answer makes sense. Okay, think about the relationship between the variables. Think about the relationship between pressure and volume, and then look at your answer to determine, does my answer make sense based on what I know about this relationship? So we're going to say 705 times 125 divided by 385, and we get a final volume of 228.9. And so we need to use significant digits here, significant figures. How many significant figures do I have in my equation here, or in my numbers? 3. Okay, I've got 3 significant figures, so I'm going to have to take my answer, 228.9, to significant figures, which gives me what? 229 milliliters. So my volume is 229 milliliters. Does that answer make sense? Yes, it does. My pressure went down, so I should expect my volume to go up. It decreased by almost half, so my volume almost doubled. Okay, so yes, this answer makes sense. So I would say, you know what, I think I have worked this problem correctly. So let me find one that's a little bit different. All right, so here's one that's a little bit different. It says change. Okay, so whenever we're going to be doing something, changing something, 750.0 milliliters of a gas at 93.3 kilopascals to 106.6 kilopascals. Okay, and then we're going to do another one. We're going to work 3 of these. So let me jot this one down right quick. All right. So we have 750 milliliters of some gas, and we have 93.3 kilopascals, and then we're upping that to a pressure of 106.6 kilopascals. So this is my V1, my 750.0 milliliters, and my P1 would be 93.3, and my P2, 106.6 kilopascals. So again, I'm looking for my V2. Okay, so I'm going to set up my equation. P1 V1 equals P2 V2. Again, I'm looking for my V2 here, so I'm going to divide both sides by P2. So now I'm going to plug in P1, 93.3 kilopascals times 750.0 milliliters divided by 106.6 kilopascals. Kilopascals cancel. I'm left with milliliters, my unit, which is acceptable. So I'm going to 93.3 times 750 divided by 106.6. And I get 656.4 milliliters. Now, if we look at what happened here, pressure went up, volume went down. Does that make sense? Yes. When pressure increases, I should expect my volume to decrease, and it did. Okay. How many significant digits do I have? Three. So what is my answer? $656, right, because I'm going to round down, okay? So this is going to be equal to 656 milliliters, okay? So let's work one more of these. This next one, we're going to have to add an additional step. It tells me to change 250.0 milliliters, oops, 250.0 milliliters, so I know that to be my V1, of a gas And it tells me it is at standard pressure. And I'm going to change that to 782.5 millimeters of mercury. So standard pressure is going to be my P1, and P2 is 782.5. So what is standard pressure? Well, if I go back to my gases cheat sheet, 1 atmosphere is considered standard pressure. That is the volume of a gas at standard temperature and pressure, Madison, which we're going to get to, just not yet. So you're on the right track. Okay, that is standard volume of a gas at standard temperature and pressure. But standard pressure is considered to be 1 atmosphere. Okay, and so my units that they're giving me in my problem, okay, let me switch back over to my problem. The units they're giving me here are millimeters of mercury, so I'm going to get standard pressure in millimeters of mercury. So what is standard pressure in millimeters of mercury? Yes, 760 millimeters of mercury. So my standard pressure here is equal to 760 millimeters of mercury. So we had to kind of add this little extra step, if you will, because we had to determine what standard pressure was. So again, I'm looking for V2. Okay, so I write my equation. Get P2 by itself. So I'm going to say 760 millimeters of mercury times 250.0 milliliters divided by 782.5 millimeters of mercury. And so 760 times 250 divided by 782.5, and I get 242.8, but I really only have 3 significant digits because this actually, I didn't put that on there, but it has a decimal here because it's exactly 760 millimeters of mercury, so all 3 of those digits are significant. So I'm going to need 3 significant digits, so 243 milliliters. Does this answer make sense? Yes, it does, because pressure went up, not by very much, okay, but pressure went up, and so I can expect my volume to go down, and it did. Again, not by very much, but it still went down. So key thing to remember here, pressure and volume are inversely related. As one goes up, the other goes down. So if we increase pressure, we decrease volume. If we increase volume, we decrease pressure. Okay, so P1 V1 equals P2 V2. All right, so now we can look at another relationship. Okay, we can look at the relationship between temperature and volume. And this is referred to as Strauss's law. Okay. And this is the relationship between temperature and volume. Okay. And the relationship between temperature and volume is actually a direct relationship, not an inverse relationship. So Charles's law says the volume of a fixed amount, so again we've got a fixed quantity or a fixed amount of gas at constant pressure. Okay, so remember, two things change, two things stay the same. So our amount stays the same and our pressure stays the same. And so the volume and temperature are the two we're looking at. So the volume of a fixed amount of gas at constant pressure is directly proportional to absolute temperature. To absolute temperature. That's a key word here. Okay? When we say absolute temperature, we're talking about the Kelvin scale, because we're talking about our absolute zero scale. So we're talking about Kelvin. Okay? And so 0 Kelvin is equal to 273.15 degrees Celsius, and they're on a 1-to-1 basis. Okay, so for every degree Kelvin, we're essentially going up a degree Celsius. So when you're given a temperature in Kelvin, you add 273.15 to get your Celsius temperature, and when you oh, I'm sorry, negative. I forgot that negative in there. Sorry. And so when you're given a Kelvin temperature, you add to get Celsius. When you're given a Celsius temperature, you subtract to get Kelvin. Okay. And so for Charles's law, the temperature value matters. Okay. So we have to be in Kelvin for our temperature. Okay, and since this is a direct relationship, and I just realized I spelled proportional wrong. There we go. So in this relationship, it's V divided by T equals that constant K. Okay, so it equals some number. So our relationship here is a little bit different than it was with pressure and volume. Okay, this time they are directly proportional. So I'm going to go back up to my cheat sheet. Let me find it. Okay, so I'm going to go back to my cheat sheet here, and I'm going to add another equation, my Charles's law. And so we've got a little bit different thing here. V1 divided by T1 is equal to V2 divided by T2. Because they're a direct relationship, then I'm going to divide instead of multiply. So my Charles's law equation is V1 divided by T1 is equal to V2 divided by T2. Okay, and again, the thing to remember is that my temperature here has to be in units of Kelvin. Okay, still doesn't really matter what my volume is as long as my volume's the same, but my temperature has to be in Kelvin. Okay, so as volume goes up, temperature goes up. As temperature goes up, volume goes up, and then the opposite. Okay, so we have a little bit different type of relationship here. So let us work some problems with Charles's law. So let me find one. All right. Okay. So this problem says change 125 milliliters of a gas from 25 degrees Celsius to standard temperature. Okay. So we've got 125 milliliters of some gas, and we've got 25 degrees Celsius, and then standard temperature. Okay. So we've got to figure out what is standard temperature. Okay. So what is standard temperature? Well, standard temperature, just like we have a standard pressure of 1 atmosphere, standard temperature is 0 degrees Celsius. Okay. And so let me go back to your cheat sheet right quick and make a note of this. Okay. Oh, now I'm kind of, I'll run it up here. So STP, if you see this in your problems, at STP, that stands for standard temperature and pressure. Okay. So standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere, which we know we can convert, right, to all the other units. But standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Okay. So we've got this problem here where we've got 125 milliliters. That's going to be V1. We're looking for V2. It was at 21 degrees Celsius. That's T1. And my standard temp is T2. But they are both in Celsius, and I need them in Kelvin. Okay. So I need these temperatures in Kelvin, not Celsius. So I'm going, and if you forget this conversion, let me find my periodic table here. On the back of your periodic table, you have a little temperature conversion formula there, and it's got a whole bunch of different ones. If you have degrees Celsius, okay, you take your or if you want degrees Celsius, you take your kelvins and subtract 273. If you want Kelvin, you take your degrees Celsius and add 273.15. So these temperature conversion formulas are on the back of your periodic table there. And so we need Kelvin, so we're going to take our degrees Celsius and we're going to add 273.15. Now, most of the time what we do is we just say 273. We don't add the 0.15 on there. Okay, we just use 273. So what I'm going to do is I'm going to use 273. So T1, I'm going to say 25, and I've got degrees Celsius. I'm going to add 273, and that's going to give me 298 K. And for T2, I've got 0 degrees Celsius, and I'm going to add 273, which gives me 273 K. Okay, so I don't add the 0.15 on here. I use just the round numbers. It's up to you. However you want to do that. If you want to add the 273.15, you can. If you just want to add 273, you can. And as long as you're showing your work, then I'll be able to see that you've done it correctly, even if your answer is a little bit off from what, you know, my answer may be. All right. So remember our equation for Charles's law is V1 over T1 equals V2 over T2. Okay, I'm looking for V2. So what I'm going to do is I'm going to get this in a little bit standard form without all these little fractions in here. So I'm going to cross multiply. Okay, I'm going to say V1 T2 is equal to V2 T1. Okay, so I just cross multiplied here so I could get rid of my fractions that I have here. So I'm looking for V2. I want to get V2 by itself, so I divide both sides by T1. And so now I have V2 by itself, so I'm going to plug in my V1, 125 milliliters. I'm going to plug in my T2, which is 273 K, and I'm going to divide by my T1, which is 298 K. So my units of K cancel out. I'm left with milliliters, which is what I'm looking for. But let's think about what is happening. Is my temperature increasing or decreasing? My temperature is decreasing. So what should I expect to happen with my volume? Decrease, because they have a direct relationship. So I should expect to get an answer here where my volume decreases. So when I do the math, 125 times 273, and I divide by 298, I get 85.7. Okay. Now, here's where we run into some confusion over significant digits when we're working these problems with temperature. Do we go with the 25 degrees Celsius, which is 2 significant digits, or do I go with my Kelvin, which is 3 significant digits, or do I go with my volume, which is 3 significant digits? So here's what I'm going to tell you with these. It really, oh, you didn't get that. Maybe I did it wrong. Hang on. Yep, I must have hit numbers wrong. Sorry about that. Thank you. I hit some wrong numbers. Yeah, 114.5. All right. So now back to our significant digits. If we look at this problem and we say we've got 3 for our volume, 2 for T1, and really only 1 for T2, what do? How many significant digits do we use? I am of the mindset here that we use our volume for our significant figures here. So I would use 3 significant figures because my volume has 3 significant figures, and when I convert my temperatures, they also have 3 significant figures. So I'm going to use 3 sig figs here, and so my answer is going to be 115 milliliters. Okay. Something else I want to caution you on when you're working these types of problems too is that sometimes your problem may say find the volume in liters, okay, or cubic centimeters. So sometimes when you get your answer, it may not be your answer. You may have to convert. So you may have to convert to liters or cubic centimeters or something along those lines. Okay, and just keep in mind that 1 cubic centimeter is equal to 1 milliliter. So if I was converting this answer into cubic centimeters, I would say 115 milliliters is equal to 115 cubic centimeters or cc's. And then if I was taking that into liters, I would just divide 115 by 1,000 to get 0.115 liters. So pay attention to your units. Okay, so let me find another one of those and let's work another one of these. Here's one. Okay, so we have a 1.00 liter sample of argon gas. So I have 1.00 liters of argon gas, so that's going to be my initial volume. And it is heated from 20 degrees Celsius to 101 degrees Celsius. So 20 degrees Celsius is my T1 and 101 degrees Celsius is my T2. Okay, so the first thing I have to do is convert my temperatures. All right, so my T1, I'm going to say 20 plus 273, and I get 293 Kelvin. And for T2, I'm going to say 101 plus 273, and I get 374 Kelvin. I'm looking for V2. So my equation, V1 over T1 equals V2 over T2. I'm going to cross multiply to get rid of my fractions and divide both sides by T1. So that I'm left with my V2 here by itself. So now I'm going to plug them in. V1 is 1.0 liters. T2, 374 Kelvin. T1, 293 Kelvin. So I just say 374 divided by 293. And I'm going to go with 3 significant digits, so 1.28 liters. Is this what we would expect? Does this answer make sense? Yes, this answer makes sense. Did everybody get 1.28 liters on this one? Good deal. All right, so this answer makes sense. My temperature went up, my volume went up. Okay. Notice that because my units of Kelvin are kind of large and how they go up, even though I went up 100 Kelvin, my volume didn't really go up by that much. So even though you've got a large increase in temperature, your volume is not going to go up quite as much because of the difference in the scale between our volume and our temperature. Okay, so that was Charles's law. Okay, so we have another law that we're going to look at. So we're going to look at Avogadro's law. Now we've already talked about Avogadro before. We had Avogadro's number, which told us the number of atoms in a mole of a substance. And so Avogadro kind of continued his work, and he looked at moles. So he looked at moles of gases. And so what he said, so he looked at volumes and moles, or volumes really and molecules, which we can convert into moles. And so Avogadro's law says equal volumes of gases. Oh, sorry, hold on. That's his hypothesis. Let me write his law. His hypothesis was that if we had had equal volumes of gases, they would contain the same number of molecules as long as our temperature and our pressure remained constant. And so his law that was developed says this: the volume of a gas maintained at constant temperature and pressure, so we're going to keep temperature the same and pressure the same, is directly proportional to the number of moles of the gas. Okay, so volume divided by N, where N represents the number of moles, equals that little constant that we've been using. So basically, if we have the volume of a gas divided by the number of moles of the gas, we're going to get some number, which allows us, again, to get an equation. So go up to my cheat sheet, and I'm going to add another one here because I'm running out of room. So we're going to do Avogadro's law here. Okay, well, we're going to say V1 over N1 equals to V2 over N2, where our N is our number of moles. And it's a direct relationship. So as one increases, the other increases. So as the number of moles of a gas increase, then our volume also increases. Okay. So let's see if I can find one of those. I don't know if I have one of those. I don't know that I have one of those. Let's see. I don't think I have one. Well, I don't guess I have one. But you would work those the exact same way as you do the Charles's law, because it is a direct proportionality. Gay-Lussac is another one. Your book only talks about him in just a tiny little paragraph, and Avogadro built upon Gay-Lussac's work. But Gay-Lussac, he looked at the law of combining volumes. That at a given pressure and temperature, the volumes of gases that react with one another are in the ratios of small whole numbers. So 2 volumes of hydrogen gas react with 1 volume of oxygen gas. So basically what Gay-Lussac did is he looked at 3 variables. So Gay-Lussac looked at what happened with pressure and volume and the number of moles of the gas. So, I'm sorry, not pressure and volume, pressure and temperature and the volume. So, let's look at his law. He said this. So he looked at pressure and temperature and also volume. And sometimes we refer to as the combined gas law. Okay. And so we have P1V1 divided by T1 equals P2V2 divided by T2. Okay. And what we've done is we've just combined Boyle's law and Charles's law here, okay, with our pressure and volume and temperature. But in order to kind of put these together, in order to kind of get to this idea of the relationship between pressure and temperature. So we have a relationship between pressure and volume, and we have the relationship between volume and temperature. But how did we kind of come to this idea that pressure and temperature are directly related? Well, that comes from Amundsen. And Amundsen kind of gets left out. Amundsen is the one that came up with the idea that pressure and temperature are directly related or directly proportional when volume is held constant. So Amundsen is the one who kind of allowed Gay-Lussac to put all of these things together. Okay, so let me go back to my cheat sheet. Okay, and let's add Amundsen since he gets left out. Amundsen's law is P1 over T1 equal to P2 over T2. Okay, so he really looked at those two properties of gases. Okay, and your book doesn't even really mention him except for in one of the problems at the back of the chapter, but that is what he did. And he allowed Gay-Lussac to come up with the Gay-Lussac's law, or what we refer to as the combined gas law. Where we have P1 V1 over T1 equals P2 V2 over T2. Now, when you work these, you know, even though we're considering more variables here, you're going to be given 5 out of the 6. So you're still only going to be asked to find one of those. Okay, so just because we add more variables doesn't mean you're going to be tasked with finding more things. You're going to be given like your P1 V1 T1 and P2 V2 and asked to find the temperature. Okay, so that when we look at all of these different pieces of the puzzle, so when we look at all of the things that we know, okay, we have looked at pressure, and we've looked at temperature, and we've looked at volume, and we've looked at the number of moles. And we've looked at really the relationships between the majority of these. Okay. So in what we've looked at so far, with the exception of the combined gas law, we were looking at two variables and holding the other two constant. So for Boyle's law, we looked at pressure and volume as long as our amount and our temperature were constant. In Strauss's law, we looked at volume and temperature as long as pressure and the amount of gas was held constant. In Avogadro's law, we looked at volume and amount, so V and N, as long as P and T were held constant. And with Edmonton's law, we looked at pressure and temperature as long as volume and N were constant. So we've only looked at these in the context of two variables. But we can put all of these things together. We can take all of these relationships that we know about and put them together into PV equals nRT. Okay, so pressure times volume is equal to the number of moles times this constant R times temperature. So now we're actually going to have a value for our constant. Before, we've just used that K to represent some number, but R actually has a definitive value. And so this is referred to as our ideal gas law, PV equals nRT. So add this to your cheat sheet. This is the ideal gas law, where pressure, or P, is equal to pressure, and the pressure has to be in atmospheres. Okay. Volume has to be in liters. N is just equal to your number of moles, so it will be in mole. Okay. Your R is what we refer to as the ideal gas constant, and it has a value of 0.0821 liters times atmosphere divided by mole times Kelvin. And so where T is your temperature in Kelvin. And the reason why you have to have these specific units is because those are the units in your ideal gas constant. Okay. So if you have units other than atmosphere, liter, moles, or Kelvin, then you're not going to get the right answer because you're not going to be able to cancel these units out. And the idea is to cancel the units out and be left with the one unit you need. So if you're looking for N, which is moles, then you're going to be able to cancel out atmosphere, liter, and Kelvin, and your answer will be in moles. Okay. So that's the idea here, is why these units are very specific that way. And so we have to have them in each specific unit. Okay. So make sure that you write this down, because when you're working these problems, you may be given the pressure in millimeters of mercury, and a volume in milliliters, and a temperature in Fahrenheit. Okay, and so you have to do your conversions before you plug those numbers into your equations. Now, when we look at this equation, PV equals nRT, we can come up with another value that's very important to us. And Madison alluded to this earlier when she wrote 22.4 liters. That is the molar volume of a gas. So if we take our equation and we rearrange it to solve for volume. Okay. And we have 1 mole of an ideal gas at 1 atmosphere and 0 degrees Celsius. So we're at standard temperature and pressure, and we have 1 mole of the gas. So we have 1 mole of our gas. We plug in our R here, 0.0821. Now it continues, but we just round to 3 significant digits here, and that's liter times atmosphere divided by mole times Kelvin. And we plug in our temperature. Okay, it's standard temperature, 0 degrees Celsius, so it's going to be 273 Kelvin, and that is at 1 atmosphere. We can cancel those. We're left with liter, and when we do the math, we get 22.41 liters, or thereabouts. Okay, this is referred to, and we typically go to 22.4 to make it a little bit easier. That is referred to as the molar volume of a gas. So, what does that mean? That means that at standard temperature and pressure, so at 1 atmosphere pressure, 0 degrees Celsius, any gas will occupy a volume of 22.4, as long as there's 1 mole of it. So it doesn't matter what gas we're talking about. It could be oxygen, it could be nitrogen, it could be helium, it could be argon, it could be xenon, doesn't matter. That at standard temperature and pressure, 1 mole of any gas is 22.4 liters. Okay. And we can use that in stoichiometric calculations. Just like we did with molar mass, we can use molar volume of a gas. But again, we're talking here of a gas. This only works on gases. Okay? Only works on gases. All right, let's do an ideal gas problem. Let's look at the bottom of page 409. Calcium carbonate, CaCO3, the principal compound in limestone, decomposes upon heating to calcium oxide, solid, and carbon dioxide gas. A sample of calcium carbonate is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of carbon dioxide gas were generated? So let's look at what we have and write down everything we have. We have a 250 milliliter flask. We have a pressure of 1.3 atmospheres. We have a temperature of 31 degrees Celsius, and they want to know how many moles. So we have a volume, we have a pressure, we have a temperature, we're looking for moles, we know what R is because it's a constant, so this tells me that I have to use the ideal gas law. Okay. Now, I've got P and V, I know R, I know T, I'm looking for N, so I'm going to divide both sides by RT so I can get N by itself. Okay, so my equation is going to be PV divided by RT equals N because that's what I'm trying to solve for. Can I just plug in these numbers? No, why not? Why can't I just plug them in as they are? They're not in the right units. Okay, so temperature needs to be in Kelvin. All right, so I've got to change temperature. What about pressure and volume? Okay, so I have to change the volume to liters. What about pressure? Pressure's fine. It's in atmospheres, and that's what my unit has to be in. So pressure is fine. So I have to change my volume, and I have to change my temperature. Okay, so 250 milliliters. I need that in liters. 1 liter is equal to 1,000 milliliters. So when I do math or move my decimal here, I get 0.250 liters. Okay, and then temperature, I'm going to say 31 degrees Celsius plus 273, and that gives me 304 Kelvin. And then I can leave my pressure alone. So now I can plug these in. Pressure, 1.3 atmospheres. Volume, I've now converted to liters, 0.205 liters. My R is a constant, 0.0821 liter times atmosphere divided by mole Kelvin. And my temperature, 304 Kelvin. So let's look at our units. Atmospheres cancel. Liters cancel. Kelvin cancels. And I'm left with moles, which is what I want. That's why you have to put these in the correct units. If you didn't have these in the correct units, then your unit would be all over the place. It would not just be moles. So I say 1.3 times 0.250. And then I divide that by 0.0821 times 304. And I get not what the book got. I must have typed in something wrong. Hang on. All right. There we go. Equals 0.01302, and my unit is moles. So how many significant digits do I need? Yes, I just need 2, because looking at my volume there, when I have a 0 at the end and no decimal here, then I only have 2 significant digits, here and here. Atmospheres, my pressure has 2, my temperature 2, so I'm going to use 2 significant digits. So this is going to be 0.013 moles, because remember, this 0 is not significant. So I'm going to use the 1 and the 3 to be my significant digits. So my answer here is 0.013 moles. Okay. Now, sometimes when we are working these ideal gas law problems, you may be given something like this. 5.44 gram sample of argon gas has a pressure of 2.7 atmospheres at a temperature of 100 degrees Celsius. What is its volume? Okay. So a 5.44 gram sample of argon gas has a pressure of 2.7 atmospheres at a temperature of 100 degrees Celsius. What is its volume? All right. So we've got the pressure, 2.7 atmospheres. Okay. We want to know volume. They are clear in that. What is its volume? And then we have temperature. 100 degrees Celsius. We know R, it's our constant. 0.0821 liter times atmosphere divided by mole Kelvin. What about N? Do we have N? Oh, my screen froze. Hang on a second.